It's amazing that from just drawing a right triangle and coming up with those 6 functions, we create this huge branch of mathematics, all based upon these trigonometric functions, these 6 functions. And if you're looking down the road, thinking about the future of what's going to happen in your mathematical life, we have the 6 trigonometric functions. And when you get into calculus, you're going to have 6 more. They're called the hyperbolic trigonometric functions. And then each of these have inverses also. So you start to get this huge pot of functions, and it gets a little overwhelming. So we spend most of our time in this class with the trig functions, the 6 trig. All right, so Pythagorean identities. I think I'll try and motivate this with a picture. Let's go with this again. A, B, C. Let's call this angle theta. All right. Now, this is not really, this is kind of a cheating way of showing you this, but it saves some time. Can you tell me what sine squared theta plus cosine squared theta is? I'm just throwing it out there for you. I just want you, oh, wow. I should have told you what the notation was first. Sorry. Scratch this. What is sine theta, then square it, plus cosine theta, then square it? 1? Okay, why? You've heard that, right? You've learned it. Good, it's burned in. That is correct. No one taught you wrong there. So I'm not here to undo everything you learned. That is correct. This is 1, but let's try and see why it's 1.
Is it like a circle?
It can come from a circle. Yep.
I know why.
Yeah. No, you have it right, but let's try and actually see why it's 1. All right? So can you tell me from our picture what is sine of theta here?
B over C.
It's B over C, right? Agreed? Okay, so this is B over C, but then I'm going to square it, right? Plus, okay, now what's cosine theta?
A over C.
A over C. And then I'm going to square it. And I'm asking you, what is this equal to? All right, let's square. When you square a fraction, you can square the top and bottom, can't you? All right, this is B squared over C squared plus A squared over C squared. Y'all still good with that? All right, can you do anything with those 2 fractions?
Make them 1.
They can make them 1, right? Because they have the same denominator, don't they? So put them together. And what do you get here?
B squared plus A squared.
B squared plus A squared over C squared. Okay, good. Now, go back here. What is A squared plus B squared?
C squared.
Isn't A squared plus B squared C squared?
Yeah.
So isn't that numerator really C squared? Right? This is C squared. And C squared over C squared is 1. So what you get is your first Pythagorean identity. It says that if you're given a triangle, right triangle, and an angle theta, that this is always true. Sine of theta squared plus cosine of theta squared will equal 1. So I'm going to just put that here. I'm going to box it. And you need to remember that the way, what was your name, ma'am? Sophia. The way Sophia spit that out, that's 1. That it should be like hardwired in there. It should be like breathing. You don't even think about it. It's the most fundamental Pythagorean identity we have. Now, there is some notation that we need to get clear, because the book will not write it this way. And I accidentally wrote it down that way when I started, and I apologize. When we want to say sine of theta then squared, here's the way we write this. Sine squared theta. We put the squared here. Plus, and then here, cosine squared theta equals 1. That's the way you'll see it in a book. But please understand that the squared here means this. Squared here means this. Not to be confused with this. What do you think the difference is between those two? That's right. This means square the angle and then figure out what sine is. So if you write it this way, there's really like a parentheses right there. This means the parentheses goes around the sign, and then you square. So it changes the order of operations. Make sense? Sure? Okay, the Pythagorean identities. Let's continue. I'm going to leave that one on the board right here. There are two more Pythagorean identities you should know. Now, the next two, I don't necessarily think have to be hardwired. It would be nice if they were, especially in Cal 2. It's nice if you have all of them, all three of the Pythagorean identities up here. But this one, for sure, these next two, you can live without them. Now, the way we get them is actually pretty clever. You can start with this, as long as you know this one. And the first thing you do is you divide every term by sine squared. All right? So I'm going to take this sine squared. I'm going to divide sine squared, sine squared, sine squared. And let's see what happens. So take that identity. What happens when I divide sine squared theta divided by sine squared theta? Then I'm going to take cosine squared theta and divide it by sine squared theta. And then I'm going to take 1 and divide it by sine squared theta. Well, what's the first one over there?
1.
1. Okay. Now this one, please understand that this is really cosine theta over sine theta squared. That's the same thing, right? And this one is 1 over sine theta squared. But what is cosine theta over sine theta? Cotangent. So this is really 1 plus cotangent, and watch the way I write this, squared theta. That's this. And what is 1 over sine? Cosecant. So this is cosecant squared theta. That's your second Pythagorean identity. And the last Pythagorean identity, how do you think I get the last one? Divide this by cosine squared theta. So start back here again, and let's try it. I'll do that over here. So take this, we're going to go sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. And so following this similar pattern, sine over cosine is tangent. So this is going to turn into tangent squared theta plus 1 equals 1 over cosine is secant, so secant squared theta. Boom. Now these are in your book. They're on most of the formula sheets. All right, I think that's good. All right, we're going to switch gears, do something a little different now. Y'all ready? Not yet? Let's say that I tell you that the sine of some angle is 3 over 8. And I tell you that the angle is acute. then can you find the remaining 5 trig functions of theta? That means, can you find what cosine theta is, what tangent theta is, what cosecant theta is, what secant theta is, and what cotangent theta is? Yeah, we can, but how are we going to do it? So since this section is called right triangle trigonometry, right, we are going to start by trying to draw a right triangle. Because remember, in a right triangle, if you have a right triangle, the 2 smaller angles have to be acute, don't they? So I'm going to try and generate this. I'm going to kind of try and draw a triangle that matches the information I'm given. So here's a triangle, right triangle. I'm going to label this angle theta, because theta is given. And then I'm going to use the 3/8 to help me draw the rest of the triangle. And if you remember SOHCAHTOA, right, sine is opposite over hypotenuse, you could draw your triangle like this, 3 and 8. And would you agree that this triangle matches this information? Yes? This triangle is really important. This is what we call a reference triangle. A reference triangle is, think about, trying to think about the word reference. A reference, something that you use to reference something that you go to get information, right? Like you're going, let me go reference Google or Wikipedia so I can find out some incorrect, right, information. But you reference something. When you draw a triangle to help you solve a problem, it is a reference triangle. You are referring to a triangle that you are creating out of your mind and out of the given information to solve the problem. This triangle was not provided for us, not directly. So once I have this drawn, I'm right back to where we were a minute ago, right? All I need to do now is figure out what this side is. If I can figure out what this side is, then I can get all the trig functions. So let's quickly figure out what that side is. Root 55. I'll do it in red because, again, this would be scratch work I would do on the side. I'm not doing this on the side, and I'm hoping that that's not too much of a stretch. If this is, just put a little asterisk next to it and ask me about it later. I told you I haven't taught the pre-cal in a long time, right? I told you all that? No. I didn't tell you that at the beginning? Yes. So I'm having a hard time figuring out where your level is, okay? So you just need to let me know, because I don't want to like baby you, but at the same time, I don't want to blow you out of the water. I feel like I'm more on the baby side right now. Y'all feeling that too? Y'all okay with that? Okay. All right, so this is okay. Now we just crank out the formulas. So sine we've got, cosine would be root 55 over 8. And then tangent, 3 over root 55. And in case I didn't tell you, you can never leave a radical in the denominator. No, I'm kidding. You can leave it just like that. And then the others, let's see. What's the reciprocal of sine?
Cosecant.
Cosecant. Now, does anyone have a clever way of remembering that? I have a way, but I don't think it's clever at all. I always remember cosecant is the reciprocal of sine because I compare it to this one. I know it's one of these. That's the way I remember. I know it's one of those. I always just look at the middle letter. And the one that has the S is the sine one, and the other one's not. Okay? All right. It works for me, but it doesn't make any sense as to why I'm doing that. 8 over root 55. And then cotangent is root 55 over 3. Did I get this right? 3. I'm not even paying attention to what I'm doing. Flip that over, flip that over, flip that over. Okay, we're good. I'm curious if anyone has noticed anything about sine and cosine, like the actual numbers. When you do sine and cosine, like this number right here can never be bigger than what? Think about this. If I draw a triangle, right? No matter how I draw it, If I'm looking at sine, I'm taking this number and dividing by this number, right? That ratio can never be bigger than what? Why can't it be bigger than 1? This is the hypotenuse, right? This side has to be bigger than this side, or at the worst, the same, right? And that's going to turn out to play a role later on, is that we have some bounds on how big sine can be, all right? I'm just wondering if anyone has ever noticed, or have you noticed that pattern? 3 over 8, that number has always been smaller than 1. And then if you reciprocate that cosecant, this number then on the other end, like flip over the logic, has to be always bigger than or equal to 1, right? This number. So it'll be interesting when we start graphing these, because we're going to start to see those patterns when we graph them. All right. That was a pretty straightforward problem. All right, let's do something a little bit more challenging. How about this one? Same instructions, okay? Same instructions. I'm going to change this to tangent. And I'm going to change this to root 3. Root 3. So reference triangle again. And when you draw reference triangles, you don't ever have to like be perfect with your picture. In other words, like if you turn out calling this side 100 and this side 2, like no one's going to get mad at you that that doesn't even look close to being that scale, okay? What's important is the relationships between the sides. Right, so don't worry about trying to get the measurements of these lengths right. Okay. Ooh, tangent is root 3. So
The opposite would be root 3 and the adjacent would be 1.
yeah, so this is opposite over adjacent, but it's not given to us like a fraction, but we can create the fraction. We can just, you can do this with any number, right? Over 1. So now you've got opposite over adjacent. So you just call this side root 3. You call this side 1, and that works, right? Now for this one, I think I'll actually solve for this side over here. We'll call it c equals, let's do it here, 1 squared plus root 3 squared is c squared. So we get 1 plus 3, which is c squared. So 4 is c. So no, c squared is what I meant to put, and then c is 2. That worked out nice. Now this is like, remember the 3, 4, 5 triangle? That I called it a Pythagorean triple. This is a very common set of numbers to have in a. This is going to come up a lot, but it's not a Pythagorean triple. What makes Pythagorean triples is that they're integer numbers. This root 3 is not an integer.
It's just a nice Pythagorean triangle.
It satisfies the Pythagorean, but it's not a Pythagorean triple. All right, now once we have that, we can do all the trig functions, right? Okay, so I'm going to let you do that yourself. I'm not going to do it, and you don't do it right now. The key to the problem, the reason I want to show it to you is that when you have just that, you can still set up a fraction. All right, good. Now, I'll be honest. I've told you I teach the calculus sequence. I can't think of a single time I've ever used this theorem in those classes. Okay? So I'm just being real with you. This is in the book. Some of your homework is based on this, but usefulness later, I've never seen it come up and really bear any fruit, really. Not to say that it won't at some other point, but all right, so let's draw. I need to draw this exactly the way they have it, so I make sure they call this A, this B. So that makes this little b and this little a. Okay. We need to know, first of all, what are complementary angles?
Two angles that add together that make 90 degrees.
That make 90 degrees.
Supplementary.
Okay, supplementary add up to be 180. So complementary angles are angles that add to be 90. I'm just going to put that here. Add to be 90 degrees.
Which A plus B in the right triangle is that?
That's right. And in any triangle, any right triangle, these two angles then must be complementary, right? Those two angles must add up to be 90 because this is already 90 and they need to add up to be 180. So this theorem says basically if you have a right triangle like this, then sine of A is equal to cosine of B. What?
Well, yeah, because it's the same function.
Okay, yeah, so what is sine of A? Just by definition, let's label this side C.
A over C and then
It's,
cosine of A.
this is just A over C, right? It's the opposite over hypotenuse. But then when you look at cosine of B, here's B, cosine is adjacent over hypotenuse. It's also A over C. So it checks out. Just be careful. We're not saying that sine of A equals cosine of A. We're saying sine of A equals cosine of B, so long as these two were complementary. And you can imagine that it works out like all of them work out this way. And there's a table on page 525. I'll just point out the most important ones. How about this one? What about tangent of A? What do you think its relationship is with B? Capital B. So what would tangent of A be? Little a over B? So in terms of capital B, how do I get that relationship? This over this. If we're looking at B, what's this over this? What's adjacent over opposite? No.
Cosecant.
Cotangent. 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 Right? You could draw these, right? Tangent of A over B. Cotangent of B, A over B again. Now these identities lead to something, or this theorem leads to something that is used quite a bit, and that's the following. All right. So I'm just going to reference page 525. If you want to look at the complete list of all of these complementary angle theorem results. Okay, so if we have, what do they call it? They don't have a name for this really. Sine of an angle theta. Now we said that sine of an angle should be equal to cosine of the other angle in the right triangle, right? Isn't that what we said? If you take this angle here and take the sine of it, it should be equivalent to the cosine of that angle. Yeah? But isn't B really the same as 90 degrees minus A? So if these are complementary, we know that A plus B has to be 90 degrees, right? So if I wanted to rewrite B, I could rewrite B as 90 minus A, right? And so that this right here turns this B into 90 minus A. So I can write this, I'm using theta instead of A, but that right there is a pretty widely used identity. And I'll write in red below it the same exact, I'm going to write in blue below it, the same exact equation, but using radians instead of degrees. So we have one for sine, and then for cosine theta, it would be sine of 90 minus theta. Same thing, same exact principle in action here. Pi over 2 minus theta. And there are 4 more listed on page 526. All right, so I'm gonna refer you to this, page 526. There are 4 more on here, and I'll just put a little star next to this because that is something that you do kind of want to know. But this right here on page 525, not so much. All right, these are far more important to know than these. Okay, this is good. How are we doing here? 15 minutes. Y'all feeling all right? I'm looking at your homework because there was one problem in there that I wanted to do one like it. Where was it? 40. Oh, here we go. Something like this. This is an example. What's 1 minus sine squared of 32 degrees minus sine squared of 32 degrees? I would like for us to figure out what that is. Now, I realize that looks like really like nothing I've put up on the board up to this point, right? That's like, whoa, where did that come from? The instructions here are to use fundamental identities and or the complementary angle theorem to somehow simplify this expression. So does anyone see anything in here that's kind of like sparking something in your mind? Yes?
What's the equation? Sine squared theta.
Plus cosine. Okay, so you see the Pythagorean identity in here somewhere. It's making you think of this? Okay, excellent. It should. And really the thing that should be making you think that is the fact that you've got sine squared, right? Sine squared, you got sine squared over there. That's the only formula I've given you up to this point that has sine squared in it, right? So you should be thinking of that identity. Now, hold on a second. I meant to change this. Hold on. Sorry. 68 degrees, 58. 58, yeah, okay. Change that to 58. These two together add up to be 90, right? Okay, we'll use that in a second. But let's go back to this identity for a second. When you have an identity, when you have an equation, you can always move things around, can't you? You can always move things around. So can I get this equation to somehow look like anything over here?
Yeah, 1 minus sine squared.
1 minus sine squared. You see that right there? 1 minus sine squared? I'm going to manipulate this, and I'm going to just subtract sine squared theta from both sides. Okay, this is just manipulation of the identity. That means anytime I see 1 minus sine squared of some angle, I can replace that entire expression with cosine squared of that angle. Agree? Okay, so let's take this right here and replace it with what? Cosine squared of 32 degrees. So this equals cosine squared of 32 degrees minus sine squared of 58 degrees. We okay with that? Now that's a legal move we just made. We're totally allowed to do that. But does it allow us to do anything else? I mean, like, can we do anything from here? Even though that was legal, it may not have been the right move. It may not get us to where we're trying to get. So, any ideas? Look at the identities I set for you to put a star next to that were going to be important. Somebody pointed out that these angles add up to be 90, right? Which identity did I give you that had like 90 degrees in there? The complementary one, right? Didn't we have this? Sine of theta equals cosine of 90 degrees minus theta? Don't we have that? So let's just mess with this. Sine squared of 58 degrees. This really means, just so we're not getting confused with that squared, this really means sine of 58 degrees squared, right? Sine of 58 degrees. Let's try that formula. Sine of 58 is cosine of 90 minus 58. What's 90 minus 58? 32, right? So can't this right here turn into cosine of 32 degrees? Can't it? According to that. And that's still what? Squared? And then out here, what do we have? Cosine squared 32 degrees, right? Which just equals 0. Because these mean the same thing, don't they? So this is cosine squared 32 degrees minus cosine squared 32 degrees, and that's 0. Does that make sense to you? Okay, you want to start from the top and just work through?
Like how you got to the 32 right there.
This right here. Okay, so look at this right here and just go into this formula. If I put sine of 58 degrees, according to this, it's cosine of 90 minus 58. So that's cosine of 32 degrees, right? That's why I had to change the problem in the beginning when I had accidentally put 32 here. So, oh crap, this isn't going to work. If I put 32 here, it's not going to work. I needed that to be 58 so that it would change over to 32 later. Did that clarify that?
Yeah, just needed this here.
This right here? Okay, good.
So if we have a problem like this, every time the answer is going to be 0?
No. I mean, well, if it looked exactly like this, and you change that to any angle and you make that like, 90 minus.
End up to like add up to 90 anyways.
Yeah, if these add up, but I mean, if we change that to a plus, it's not going to be the same. You know what I'm saying? It had to look exactly like this. So your homework, there's a couple of problems in there like this, where you have to use some identities and mess with it. So I didn't want to just throw you to the wolves with that one. We've got 5 minutes. So since we have 5 minutes, and I need to pass around the sign-in sheet, that you should be okay with the homework from what we've covered. You should be able to handle it. What did I talk about? I talked about that adding up the numbers at the end of class last time, right? The kid? Okay, so I've got another one for you while you're signing in. I was asking my math for business class this today. Okay, does anybody know what the number is right next to 1? So you have the number 1 on the number line, right? What's the number right next to it? Yeah, it's smaller than 1, but what's the number? Point what? 0.99? 0.999 forever? Does that seem like a good candidate for this? That seems reasonable, doesn't it? Yeah? Okay. So, give me at least 3 or 4 minutes. Let me see if I can spark your interest here. So here's number 1. It's being proposed by several students in the class that the number right next to 1 is 0.999. This comes up because if you look at, remember this notation like 0, 1 versus 0, 1 with a bracket? Like what's the difference between these two? The bracket includes the 1, parentheses says excludes the 1.
It's every number up to 1, but not included.
Up to 1, not included. So why not just put 0.999 repeated with a bracket?
It just gives it an easier way to write the notation.
Right. Okay. So does it seem reasonable to you that this number right here would be the number closest to 1? Anyone skeptical that maybe it's not? Okay. So let's see if I can kind of get you to scratch your head here. All right. All I'm going to do here is algebra, all right, everyone? And you're just going to tell me whether or not you agree, whether or not the step I do is correct or incorrect. You ready? I'm defining x to be 0.999 forever. That's x. Everyone got that? Okay. What happens when you multiply a number by 10? What happens to the decimal point? Decimal goes one place to the right. So, do you agree with this? If this is true, then 10x should be 9.999 forever. Still good? Yep. Okay. Now I want you to look at this from 2 different perspectives. First of all, algebraically. Algebraically, if I ask you right now, what's 10x take away an x? What would you tell me it is? 9x, right? Forget what x's are. Just if I say algebraically, 10x's take away 9x's, I should always get 9x's, right? Now, let's look at what I've stated here. If x is this, everyone agreed with me that 10x is this, yes? So what's 10x? Let me not write 10x. Let me write down. What was 10x here? 9.999 forever. If I subtract from that x, 0.999 forever, then what would you get? Just 9, right? Yes? So, do you see what you just said? What you're saying? We said that x was this. Everyone agreed with me that 10x was this. We showed that anytime you take 10x's and you subtract 1x, you should get 9. But when we actually did the computation of 10x minus x, we got 9. Which means that these two have to be equal, right? These two have to be the same, don't they? 9x's have to be 9. Which means x has to be 1. Which means this is the number 1. That is not the number closest to 1. That is 1. So 0.999 repeated forever is 1. Sorry, I'm here to confuse you. All right? That means that there is no number. If you try and find a number, so if I go in here, I go, and imagine I'm standing on the number line, right? And I'm standing at 1. And I try and just step out to the next number, right? As soon as I put my foot down on a number, I'm going to realize that I actually missed a bunch of numbers. In fact, there's an infinite number of numbers that I will have missed. It's impossible to actually have a number. There is no closest number to 1. It just doesn't exist. As soon as you find it, imagine you said that it was 0.8, even though it's not. Okay? What if you said 0.8 was the closest to 1? All you'd have to do is take the average of these two. Add them up. What are those added? 1.8, then divide by 2, and you get 0.9. 0.9 would be even closer. But then you would just take the average of those, right? Add them up, divide by 2, you would have another one. So you go ahead. You tell me what you think the closest number is. I'll always find one closer.
It could be a half of a half of a half of a half of a half
Forever.
of a half of a half.
That is why we have to use this notation, because there's no way to actually say what the number closest to 1 is. Even though this is looking like the best candidate, turns out that that is 1. Anyway, okay. Everyone sign in?
Seen them do the sheet of paper fold thing? Fold the sheet of paper on YouTube. They
Oh.
fold it until they fold it like 36,000 times, and they prove to you that they can make a 1 millimeter sheet of paper reach the moon. It folds in halves.
Oh, was it like theoretically?
Yeah, well, no, it actually shows you that it's confirmed that there's an infinite number of spaces in between the halves of the halves.
Gotcha, sorry.
There's no